Sam is inviting 7 friends to his birthday party, and he is planning to give them color pencils and candies as the return gift. He has 21 color pencils and 35 candies in all. Now, Sam wonders how many candies and pencils he must pack in each return gift so that all his friends get an equal share. Sam recalls the divisibility test of the number 7 and found that he can pack 3 pencils and 5 candies for each of his friends. Now, similarly, can you figure out whether a polynomial divides other polynomial without actual division? For example, can you find out whether x plus 3 is a factor of the polynomial x squared plus 5x plus 6 without actual division? We can definitely find the remainder when x plus 3 divides the polynomial x squared plus 5x plus 6 using the remainder theorem. Let us first recall the remainder theorem. It states that if a polynomial p of x of degree greater than or equal to 1 is divided by the linear polynomial x minus a, then the remainder is given by p of a for any real number a. So the remainder when polynomial p of x equal x squared plus 5x plus 6 is divided by x plus 3 will be given by p of minus 3. So we get p of minus 3 equal to 0. So x plus 3 is a factor of the polynomial x squared plus 5x plus 6. This special case of remainder theorem when the remainder is 0 is called the factor theorem. We shall not only learn the factor theorem and its converse, but also apply it to find the factors of various polynomials. Any polynomial of degree, say n greater than or equal to 1 and a is any real number, then x minus a is a factor of the polynomial p of x if p of a is 0. Given a polynomial p of x whose degree n is greater than or equal to 1, and a is a real number such that p of a is 0, we have to prove that x minus a is a factor of p of x. Let us prove this theorem. Let q of x be the quotient and let the remainder be r, when polynomial p of x is divided by x minus a. Applying division algorithm, we get p of x equal to x minus a into q of x plus r. By remainder theorem, when a polynomial p of x is divided by x minus a, the remainder must be p of a. From equation 2, using r equal to p of a in the equation 1. Since it is given that p of a is 0, therefore p of x must be equal to q of x into x minus a. So x minus a is a factor of p of x. Hence, we have proved the factor theorem. Now, let us see the converse of factor theorem. If p of x is a polynomial of degree greater than or equal to 1 and a is any real number such that x minus a is a factor of the polynomial, then p of a is equal to 0. Here we are given x minus a is a factor of the polynomial p of x whose degree is greater than or equal to 1 and a is a real number. We need to prove that p of a is 0. Let q of x be the quotient and r be the remainder when p of x is divided by x minus a, such that p of x is equal to x minus a into q of x plus r. Now, let us substitute x equals to a in p of x. We get p of a is equal to r. Since x minus a is the factor of p of x, hence the remainder r must be 0. Since r is equal to p of a, so p of a must be 0. Hence, we have proved the converse of factor theorem. Let us use factor theorem to examine whether x plus 4 is a factor of the polynomial x squared plus 9x plus 20. Let the polynomial x squared plus 9x plus 20 be equal to p of x. us now substitute x equal to minus 4 in p of x. On simplification, p of minus 4 is 0. So x plus 4 is a factor of the polynomial x squared plus 9x plus 20 using factor theorem. We are already familiar with the factorization of a quadratic polynomial of the type x squared plus L into x plus m by splitting the middle term. Recall that in this method we split the coefficient of the middle term into two constants a and b such that their sum and product is equal to the coefficient of middle term and the constant term respectively. Let us illustrate this method by an example. Let us factorize the quadratic polynomial x squared plus 4x plus 3 by splitting the middle term. Notice we can express the middle term 4 as the sum of 3 and 1, and the constant term 3 is also the product of 3 and 1. Now let us substitute these factors in the polynomial and split the middle term. Finally, here we have factorized the polynomial as x plus 3 into x plus 1. Now, let us move one step ahead and use the method of splitting of middle term to factorize the quadratic polynomial ax squared plus bx plus c. Notice that in the earlier example, we have the leading coefficient a equal to 1, but now the leading coefficient can assume any non-zero real value. Let us assume that the polynomial ax squared plus bx plus c can be factorized in two linear factors, px plus q and rx plus s, for some constants p, q, r and s. So according to the factor theorem, the polynomial ax squared plus bx plus c must be equal to the product of px plus q and rx plus s. Next, let us open the terms inside the brackets on the right hand side and simplify the product. To maintain the equality on both the sides, we need to compare the coefficients of like powers of x. Notice that the middle term of the polynomial ax squared plus bx plus c is the sum of two numbers ps and qr. Also observe that if we rewrite the product of ps and qr as pr into qs, then it is equal to the product of a and c by splitting the middle term. On comparison with standard quadratic polynomial ax squared plus bx plus c, we have a equal to 3, b equal to 10, and the product of a and c equal to 9. Notice that we can express the middle term 10 as the sum of 9 and 1, the product of which is 9 also. Now let us substitute these factors in the polynomial and split the middle term. Finally, here we have factorized the polynomial as 3x plus 1 into x plus 3. Let us see the steps required to factorize any polynomial p of x of degree more than or equal to 2 using factor theorem. First, find out all possible factors of the constant term of the polynomial p of x. For the factors of constant term, evaluate the polynomial p of x. Select those values among the factors of constant term, say f1, f2 and so on, for which the polynomial p of x becomes 0, since f1 is a 0 of the polynomial. According to the factor theorem, x minus f1 must be a factor of the polynomial p of x. Continue this till all linear factors are obtained. Remember, the number of linear factors will at most be equal to the degree of polynomial. If required, find the other factors of the polynomial p of x by division of polynomials. Factor theorem to factorize x squared plus 3x plus 2 into two linear factors. Observe the constant term 2. Factors of 2 are 1, 2, minus 1 and minus 2 respectively. Let us evaluate the polynomial for these factors. Observe the value of the polynomial x squared plus 3x plus 2 is 0 for x equal to minus 1 and minus 2. So, as per the factor theorem, x minus of minus 1 and x minus of minus 2 are the factors of the polynomial x squared plus 3x plus 2. Since the degree of polynomial is 2, so it cannot have any other linear factor, but it can have a constant factor. So polynomial x squared plus 3x plus 2 is equal to the product of two linear factors given by x plus 1 and x plus 2 and constant k. On comparing the coefficient of x squared in both sides, we get k equal to 1. So, the polynomial x squared plus 3x plus 2 is equal to x plus 1 into x plus 2. Use the factor theorem to factorize the cubic x cubed plus 2x squared plus mx plus 30, given that x plus 6 is a factor. Since it is given that x plus 6 is a factor of the polynomial x cubed plus 2x squared plus mx plus 30, so according to the factor theorem, x equal to minus 6 will satisfy this cubic polynomial. So before we factorize this polynomial, let us find the values of unknown m. Let us substitute x equal to minus 6 in the cubic polynomial. Next, simplify the various powers of minus 6 on the left-hand side. Simplify the arithmetic expression and merge constants in left-hand side. Transpose 114 to the right-hand side. Divide by minus 6 to both the sides to obtain m. Here we get m equal to minus 19. Let us put the value of m in the cubic and divide by the given factor x plus 6. Here we get the quotient as x squared minus 4x plus 5. Observe that the quotient is a quadratic polynomial which we cannot further factorize by splitting the middle term, as there are no two numbers whose product is 5 and sum is minus 4. Hence, the only simplified form of polynomial x cubed plus 2x squared minus 19x plus 30 is the product of x plus 6 and x squared minus 4x plus 5.